So this is problem 1, memory concepts. And our first question is asking to rank by lookup time or hit time, fastest to slowest for these types of caches. So our fastest is direct map cache because we only read and compare one tag, followed by 4-way set associative, because we are reading 4 tags in parallel to determine which one. And then finally, a fully associative is the slowest because we have to compare against every line. And if we have more associativity, we can buy fewer conflict misses, but at the cost of hit time. So that's why this is going to be the slowest, fully associative. Okay, next is we're reading a 10 megabyte array sequentially and exactly once. And we're asking which mistype dominates. So that would be compulsory miss. Why? Because a single sequential pass touches each block exactly once. So each block's first touch is unavoidable. And we can eliminate the other two because of this statement right here. We're only looking at it exactly once. And so doubling associativity does not reduce these types of misses. And what helps is larger blocks. Bringing in larger blocks means we can bring in more neighbors, sort of thing. So one miss can bring in useful neighbors. Or we can prefetch. That also can help. All right, part C. Which one requires a dirty bit? That would be our write back. Because we're deciding on eviction whether to write the line out or to just drop it. Part D, true or false. A TLB miss is always causes a page fault. False. TLB just has to do with the translation being cached or not, but the page might be actually there and we can walk the page table to find it or not. And we're asking, is it a page fault? Does it imply that the page is not in the TLB? Technically true, because if it's not even in the page table, then it can definitely not be possible to have a valid TLB entry. Part E, we're asking if I power off my computer, what loses contents, and we have some options here. And so this has to do with volatile and non-volatile memory. So our register file, our SRAM, our DRAM, main memory, are all they're all volatile, meaning if I turn off my computer, they go away. And our disk persists. That's non-volatile. So even if I turn it off, I'll still have that. On a write miss, which write policy does not bring a block onto the cache? That is going to be our write no allocate. We send the write to the next level and we do not load in the block. G, we're looking at a VIPT cache, virtually index physically tagged cache, and we are asking the max number of sets we can have with no aliasing. So our rule, remember, is K plus B has to be less than or equal to P. Remember, K are our index bits, which are important. B, block offset bits, and P are the page offset bits. So we can solve for K. We get K equals P minus B. K is less than or equal to P minus B. So the most index bits you're allowed is P minus B, or less. So remember that sets is equal to 2 to the index bits, right? So 2 to the K, and K here is P minus B. So to maximize the sets, use the maximum. K equals P minus B. That's the maximum value you can have for K. So our max sets, I'll write max sets here, equals 2 raised to the P minus B. That'll be our maximum number of sets. And so if I exceed this, then the top index bits that we have actually come from the translated VPN. So that'll lead to aliasing. So if we exceed, then we can have 2 virtual addresses by accident mapping to the same physical address, or to the physical line. And we can land in 2 different sets by accident, even though it's the same VA. And so we have a design question here where we have a hit time of 1 cycle, miss rate 10%, penalty, and we redesign to match this criteria. And we're asking, is that worth it? So we just plug the numbers into our AMAT formula. And the original had 1 cycle plus 10% times 20, which is our miss penalty, times miss rate. We get 3. And this is design 1. Design 2 is going to be halving the miss rate and doubling the hit time. So that would be 2, doubling that, plus 0.05 times 20, and that is also 3. So they equal each other. So we don't need this design choice. It's not worth it. It's not doing anything. And last question. Increasing the block size reduces compulsory misses, like we saw here. Yet, beyond some point, the overall miss rate rises. Why does that happen? And give 2 reasons. So I would say the first reason is that if you have a fixed capacity, bigger blocks in a fixed capacity means that we have fewer blocks. Fewer blocks means that there's more chance for increased conflict capacity misses. And another reason is that if you have bigger blocks, you might bring bytes that are unused. Or maybe we could be wasting space and possibly evicting useful data. So these are some downsides of bigger blocks.